That's right, it's fade in and fade out. So this is not done using PWM technique, it's done using BAM, bit angle modulation. So BAM is better compared to software PWM. You use those techniques when you run out of hardware PWM pins. So generally you'll have 6 or 8 hardware pins depending on the microcontroller that you're using. But if you want to have more than 6 or 8 channels, these techniques would be viable, because why we use BAM is to have better CPU overhead compared to software PWM. In software you can implement to dim the LED brightness, but in BAM you can do it the same thing, but the processing overhead will be less. So you can dim the LEDs for almost all the pins. You can use any pins, any GPIO pins. So currently this is running on 80 mega 1284p clocked at 20 megahertz, and so if I see it in a logic analyzer software, mm, to visualize it, I have captured it in the logic analyzer. So as you guys can see, this is not PWM, this is different, this is BAM. So this is on time, off time, on time. So as I go along with the time, you guys can see that it's incrementing, right? Yeah, it's incrementing. The binary numbers increase, as I'll explain shortly. So if I keep going, the wait, okay, yeah, one moment please. Okay, yeah, the timings do change. So to visualize it correctly, I have a website open here. Wait, so to visualize it, this is the website I want to show you: christian-marty.ch. So this is a really cool website. He explains everything about bit angle modulation and everything. So yeah, so there is one feature about this website, this one. Yeah, so here I can change the PWM value and it will visualize the on time and off time. So what you can see here is pulse width modulation, PWM. So this is a bit angle modulation, BAM. So if I have like 50% duty cycle, which is like 128, if I go to 128, yeah, almost, let's do 129. Yeah, so for 129 in PWM it's on time 50%, like 129 out of 255, and then after 129 counts, like in a counter you turn it off for half of the time. When it comes to BAM, what you do is you get this number 129. So to get 129 in the time period, you have to like actually do it in time. Like the on time and off time should be incorporated with the actual number. So if I have if I want to put 129, so this portion of the period is for 128 like microsecond or milliseconds. This portion of time is for 64 like 65 unit of time. This is 32, 16 and so on. So this first one is 1 microsecond. Okay, so 128 microsecond plus 1 microsecond is what, 129. So if I scroll over this here, see 1 microsecond, 2 microsecond, 4 microsecond, and yeah, 128. If you add all of this together, you'll get 255. So if you want to have like duty cycle of what, like 129, so you take 128, then for to add up 1, uh, you add this LSB bit 1. If you want to have, say, uh, um 68, you take 64 plus 8, then you'll have like this 68. How is it? Okay, it's a bit touchy. Okay, so 68, so 64 microsecond on and 4 microsecond on. So the GPIO, what it's actually doing is, so 1 microsecond it will be off, 2 microsecond, 4 microsecond on, then whatever it's between it will be off, and 64 microsecond on. Then you, after 64 is 128, so 128 microsecond it will be off. So this blank period, we can't notice it, it's so fast, we can't perceive the difference. So yeah, that's how it's done. So you go to this website and you can play along with this. The guy who made this is really good. I mean, I'm happy to see this in action. Even like if you do it in logic analyzer, like if I capture it in real time, like it's hard to visualize. Okay, it's hard to visualize here. So what you can do is you go to this website and you can learn this and implement it yourself. So I have uploaded my code in GitHub and you can go ahead and check it out. And that's it. Thank you.